Okay. So yesterday we cut short the discussion because it was getting almost an hour long, and we decided that we will continue with the illustrations for motivation today. I just want to go over a few examples which are not trivial. Right? I don't think that Jyoti is telling all sorts of easy things to lure us into the trap that DSA is easy, but it's actually really, really tough, as our seniors and other people have told us. That's not the case. These are pretty practical examples which you will encounter in your journey through DSA this summer. And I hope you find them tractable, easy, and that these will make you more confident while learning DSA. So let's get started. So I was talking about how to measure performance, because you write a solution to a problem, your friend writes a solution, but there is a major difference in the amount of time it takes to go through, let's just say, a billions of numbers. Right? While yours takes 2 minutes to do that, on the same computer, your friend's algorithm, the implementation of that algorithm takes 20 hours, right? So that's a huge difference. So it looks like your algorithm is way more efficient time-wise than their algorithm, right? But their algorithm takes way less space than your algorithm. So your algorithm completely consumes all the RAM available, but their algorithm, does it with very little RAM. So space-wise, theirs is more efficient. Time-wise, yours is more efficient. So we will be analyzing the space and time complexity of most of the algorithms that we will write in this course. Right? So let's take a small example. So this code that you see here is performing a basic linear search. So it takes an array, right? Size of the array and the element that you were looking for. And it runs a loop through all the elements of the array, starting from the array index of 0 all the way up to n-1. And if at some point the index under consideration has the element x, then we return the index and we say that element x was found at this particular location. And if you go through the loop and you are unable to find the element, then you return a -1. -1 is kind of a special number here because no array index can be -1, can go from 0 to n-1. But if you return -1, you're indicating the caller that you are not able to find that element in the array. And we've taken an example array here of 5 elements. So the indices go from 0 to 4. N contains 5 here. And you want to look for the element 10, right? And you just do a linear search. So 10 is available at the location 3 here, 0, 1, 2, 3. And if the result is not equal to -1, which it will be in this case, you will say the element is present at index 3, right? So let's analyze the performance of this algorithm. So what is the big O notation? That is the upper bound. That is the worst case, right? That this algorithm can ever need you to sacrifice in terms of time, right? The worst case. So what, according to you, can be the worst case for linear search? Anyone?
So it searches to the last element.
Correct. Very good. So the element that you're looking for is either not there in the array. So then it will go through the entire array and say that the element is not there. Even if it is there at the last index. So it has to still go through all the n elements in the array. That is the worst case. So the worst case performance of linear search is said to be O of n, right? It is linear in terms of n. So if n doubles, right, and then the time that this algorithm will take will also double, right? So it grows linearly with n. Now, what is the tight bound? The tight bound is basically the average amount of time it will take. It is neither the worst case, it is neither the best case, it is the average case. So on an average, what can you expect to happen? If you run this algorithm for, let's just say, millions of numbers, millions of times, what did you expect? At what index is the element found? Mostly around the midpoint, right? if you take random set of numbers without any bias, then you will see that the numbers are usually found after n by 2 comparisons, right? लगभग बीच में ही वो मिलेगा, उसका जो एवरेज होगा, and n by 2, so that is why it is set to, so n by 2 is like n, right? N by 2 grows linearly with n, right? So you get rid of the 2 and you say if the number of elements are doubled, so the average case time will also get doubled. So it is theta of n again. It grows linearly with n. And what is the lower bound? What is the best case here? Can someone tell me what is the best case for linear search?
Sir,
The first element.
Yes, please continue.
Element lying at the beginning of the array.
Yes, both of you are correct. So in that case, it is doing only one comparison. Doesn't matter how long the list is. The list might have trillions of elements, but if it finds the element in the first index, it says I found it. So it is omega 1. It is not related to n. It is constant time. Constant time, that's the best case. So is this kind of clear to everybody? So this is what we will do for most of the algorithms that we study in this course, right? We tell, okay, this is the worst case, this is the average case, and this is the best case. The interviewers will also ask you this. You also have to analyze the space, right? How much space does this algorithm take? Now, how much space does this algorithm take? Linear search. N elements. If there are n elements, you have to store all of them in an array. So the space requirement is n, right? It grows linearly with n. So they will ask you to do the time complexity analysis and the space complexity analysis for algorithms, and you should be able to do that. And you will learn more ways, more techniques for doing something like that. Okay, let's look at what a stack is. What do you think is a stack? So if I take a book at the bottom, right, and then I keep another book on it, then I keep another book. So I get a stack of books. Can I remove the bottom book first?
No, sir.
No, sir.
We can't do that, right? I can only remove the book at the top. But that is the book that got in last. The thing that got in first was the book, is the book at the bottom, right? So that is why a stack is called as a last in, first out, or first in, last out, right? You can call it FILO or NIFO. Both of them are correct in this regard. So you have a stack of plates or stack of books. So stack is that kind of a structure. It's useful because it mimics a lot of real world scenarios, right? So it supports a few operations, like when we write code for stack data structure. So we will implement push. What is push? You push something to the top of the stack. Like you keep a book on top of the stack. What is pop? You remove something from the top of the stack if the stack is not empty. What is peek? Peek is what is there at the top. You want to just look at it without popping it. Like what book is there at the top of the stack? You don't want to remove the book, but you want to just know what is there. And is empty, to find out if the stack is actually empty, right? So these are the 4 most common operations that you will support on any stack. So what is the usefulness of a stack? So here we study how can you parse mathematical expressions, especially how can you check if the parentheses are balanced. What do you mean by balanced parentheses? It's like every open parenthesis has a closing one coupled with it, right? There are no imbalanced ones. For example, if I remove this parenthesis here, then this guy does not have its partner. So there is an imbalance there, right? So how can we verify that a given mathematical expression has balanced parentheses? So we use a stat, right? So we encounter, let's just say something like this here. What do we do? So we first encounter this character, and since this is a bracket, we push it on the stack, right? So the stack was empty. Now it has this one parenthesis, the open parenthesis. And the second one is again a open parenthesis. We push it again on the stack. So now there are 2 here. Then we kind of ignore all of these guys because they are not parentheses. And the moment we get the closing parenthesis, so we pop. What do we pop? We pop this guy here. It's like we found your partner, so you both can get out. Right? So now what is remaining is this guy. This, the first parenthesis that we had encountered. And then the moment we encounter the second closing parenthesis, we pop this out, this one also. And by the time we reach the end of the expression, if the stack is empty, that means the expression was properly balanced. Are you able to understand this?
Yes, sir.
So this is a very common thing, right? So they ask this
But
question.
can you just go this bracket explanation once again?
Sure, definitely. So, so when you see an expression like this, so the moment you see an open bracket, you push it onto the top of the stack. And when you see a closing bracket, you pop whatever is there at the top of the stack. Right? At the end, if the stack is empty, that means the brackets are properly balanced. So I see open, I push both of them to the stack, right? The moment I see a closed bracket, I pop this bracket from the top because you kind of found its partner, right? This guy is popped the moment you see this bracket. They form a pair, right? And this bracket is popped the moment you see this bracket.
Okay, sir.
Okay, does that make sense? Okay. So at the end, if there is nothing in the stack, that means you can prove that the stack is balanced. A real world problem, expression evaluation, and you can use a stack for doing that. Favorite question of interviewers in your interview questions.
Sir, in any case, is there any case where we have an unbalanced equation? Like here it's a balanced parenthesis. Is there any situation where we have unbalanced parenthesis?
Well, you can just remove this bracket and feed it to the program. And then what will happen is that at the end, this will remain. It will not be empty. So you can complain to the user that your expression is not balanced. Ideally, all expressions should be balanced. Right? Why would you have an expression that is not balanced? And that is an error, right? All right. So let's take an example of backtracking. What is backtracking? Have you ever backtracked in your life? It's like you wanted to do something, you did something for a couple of months, then you kind of backtrack and you say, okay, let me go back a bit, not completely 2 months back, but I will go 1 month back and I will take a different path, a slightly different path, right? Then you do something for some time and then you say, no, let me backtrack a little bit and then I'll take a different path. Right? We have all done it in our lives. We do it on a daily basis. Right? So that is called as backtrack. So this is the n queens problem. So there is a board like a chess board whose dimensions are n cross n, right? And there are n queens. So if there are 2 queens, the board will be 2 cross 2. If there are 3 queens, the board will be 3 cross 3. I mean, n queens, n cross n. So you have to place those n queens in a way, like what happens in a chess board. Like when can one queen attack another queen? Does anyone know?
If the separate queens are in front of each other or in the same diagonals as each other.
Correct. So if they're placed in the same row or column or diagonal, then they can attack each other. Right? So you have to place them in such a way that no one can attack any other queen. So they cannot attack each other. Right? So how will you do that? So this is a 4 queen thing, right? So 4 cross 4, you start with a board. Right? Then what do you do? The most logical thing is to take the first queen and place it at the corner here. Right? Then what can you do? Then you move to the second row. Right? In the second row, where can you place the queen? You cannot place the queen here. Right? You cannot place the queen here because this will make the queen appear in the same column. This will make the second queen appear in the same diagonal, in the diagonal, the first diagonal. So you put the queen here, right? Try the third column. Then you move to the third row. What do? You cannot put it here, right? You cannot put it here. Why can you not put it here? Because it will be on this diagonal, right?
Sir, we can put it in the fourth to second column.
No, I'm looking at the third row, right? We put the queens row by row, right? We put them row by row. So the first row, is fine. Second row, we will see, okay, we cannot put it here. We cannot put it here. Why? By putting it here, these two queens can kill each other. By putting it here, they will be on the diagonal. So we'll put it here. Okay. Two rows are done. What about the third row?
So there is nowhere we can put the queen safely in the third row.
Sir, in third row, if we put the queen in the first point,
Yes.
actually I was thinking that in third row we can put it in the first space, but the first row queen will kill it.
Exactly. So that is where we will backtrack, right? So look at what is going on here. So you try the fourth column here. So if you do that, it is still not safe because these two queens will be able to kill each other, right? We cannot put it here. Why? This queen is there. We cannot put it here. Why? This queen is there. We cannot put it here again because of this queen. We cannot put it here because of this queen. So that's it. We have hit a dead end, right? What do? We
So
backtrack.
can't we put the second queen on the last
Hold
point?
on. That is, I'm getting to that, right? So I'm talking about if this is already set in stone, then you explore this queen and you figure out that you have hit a dead end, right? So then what do? You backtrack. You remove the queen from the third row, fourth column, then you back up until the second row. That is called as backtracking, right? We backtrack. And what do? This queen, as you said, many of you said, cannot go here, 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 and here. It was here, right? The third column. Now we put it in the fourth column. Is this fine? Right? And then, after having done that, we go to the third row. And we figure out that if you put it here, it is going to be safe. All the three queens are going to be safe from each other. Does that make sense?
Yes, sir.
Okay. So then you move to the fourth row. Then what do? You put it here. But you tell me, is that a successful placement of all queens?
No.
No, it is not. So what would you do in this case? Is the statement true?
No.
No, sir.
It's not. So what would you do? You have any ideas?
We could backtrack from the first row. हम लोग फर्स्ट रो में क्वीन उस डायगोनल पे प्लेस नहीं करेंगे.
Okay. So your job is to actually make this statement true. Come up with the way in which this can be done. And then let me know. Okay. If you can find a solution to the n-queens problem. But do you get the idea of what we are doing here?
Yes, sir.
Right? So this is called as backtrack. So we do something and we set that in kind of stone, right? Temporarily though. Then we say that, okay, having said this, can you do something on top of that? If you hit a dead end, then you backtrack. This is mostly like depth first search, right? The one that we use to solve the maze problem. Right? So when we meet on Monday, tomorrow we're not doing a class because it's Sunday. We all want to get our sleep. It's your job to make sure that all the queens are placed successfully.
Sir, actually, we have to displace only 2 queens to make this job successful.
Okay, tell me.
Sir, in first queen, in the first row, we can place the queen in the second column. And the queen in this third row, we can place it in the third row of first column. Then the placement will be correct, I guess.
Okay. If that's what you think, then sure. Can you post it on Telegram for the rest of the people to see? And then, we can have a discussion on that. Okay?
Okay, sir.
I have one idea.
Okay. Please go ahead.
So we can place first row queen in the third column, then second row into the first column, and third row into the last column, and fourth into second.
Sure. You also post your solution on Telegram and let's see if this if both of your solutions are correct, right? And kind of, if possible, draw the entire tree. It's like start here, put the queen here, and then show that it is not going to work, right? Then you move the first queen to the second column, then, show the backtrack, like when you have to backtrack and why you have to backtrack. Then it will be clear to everybody what is going on. Make sense? Solve it like a computer would solve. A computer does not have a brain. So don't look at that and say, okay, this is how it should be. It will do it in a very stupid way, right? Brute force through all the different possibilities and figure out what is going to work. This is the n queens problem. People consider this problem to be hard for some reason, but it is not hard. If you code it up, it is not going to take you more than 20 lines of code to do this. Okay. The more courageous ones of you can actually end up coding this in C. And let's see if you're able to do that. Okay. All right. For the ones who are not able to do that, nothing to worry. You will be able to do that in a month. So we all win. Okay. So let's look at a sorting algorithm, right? Insert some sort. So what does insert some sort do? So it iterates through an input array and removes one element per iteration, finding its place in a new sorted array until no input elements remain. Right. So take a look at this. So the initial array has all these elements. So what do? We assume that the first element is already sorted. If that were to be the only element, it would be sorted, won't it be? So we'll assume that this one element is sorted on its own. Then we consider all of these elements from the second one onwards. Then we pick 3 and find a place for it. Will it go before 4 or will it go after 4? It will go before 4. So we have this sorted list and this unsorted list. Then because 3 and 4 are dealt with, we deal with 5 and we try to find a place for it. Will it go before 3, after 3 or after 4? It will go after 4. So we have this. Then we take 1. Then we find a place for 1. We insert an element in its proper place in the sorted area of the array. Right? That's why it is called as insertion sort. And we put it here. And we take the 2 and 2 finds its place here. So we have 1, 2, 3, 4, 5, which is a sorted array. Are you able to understand this piece of code? Sorry, this illustration here?
Yes, sir.
Yes, sir.
Which we do, while teaching sorting, like we do bubble sort, insertion sort, and then we move on to, then we also do selection sort, then we do merge sort, quick sort, and heap sort. Very easy, all of them, but interesting nonetheless. So what is the worst case? What is the worst case? How many comparisons do we do overall? So let's analyze the performance of this algorithm. Okay. So if there are 10 numbers, how many comparisons will you do? Do we do any comparisons? Like when we take this 3, we compare it with 4. Right? That is one comparison. When we take this 5, we compare it with 3 and we compare it with 4. When we take this 1, we only compare it with 3. That is a good thing. When we take this 2, we compare it with 1 and 3, 2. And then we figure out, okay, no. 2 is smaller than 3. So it will go in between 1 and 3. And when we insert the 2 here, what happens? We have to move 3, 4 and 5 to the right. Don't we have to? When you insert something in the middle of an array somewhere, right? A bunch of the elements to the right of the point of insertion have to move one place to the right. Isn't that true?
That's all.
Okay. So when we do that, so it's about the number of comparisons and the number of movements, right? So what is the worst case of the insertion sort thing? Can you tell me this clever case where you will see the worst performance of this sort? And how does the input have to be to reveal the worst tendencies of this sort.
So,
we'll have to shift all the elements.
a large number of elements have to be shifted.
Correct. And when will that happen? How should the input
When
be?
the number inserted is the smallest number.
Okay. Can we do better? Can we do better with the input, the description of the input, which will result in the
Descending order mein rahega numbers.
Yes. If all the numbers, so if the aim is to get the numbers in ascending order, but the input is in descending order, right? Then you will see the worst case. Okay? Then you will see the worst case. Like comparison होते ही रहेंगे और हर केस में आपको मूव करते रहना पड़ेगा. Like for the first number, you will have one movement. For the second number, you will have two movements. For the third, three. For the fourth, four. So, how many movements would be there? 1 plus 2 plus 3 plus 4 all the way up to n minus 1. It will look kind of like n into n plus 1 by 2, right? Or n into n minus 1 by 2 because you go from 0 to n minus 1. So, what is this? If you open this up, it will be the order of what? N square. Will you have an n square term over there? If you take this expression and open it up, you will get n square by 2 minus n by 2, right? So when there is n square by 2, there is no job of n by 2 there. N square by 2 is already going to be so big that n by 2 is going to be overshadowed, right? So you consider the biggest power of n and you say that it is going to have a worst time complexity of O of n squared, right? If n is 5, it takes, let's just say, 10 seconds. But if you make n as 10, what would happen? 5 is 25, 10 is 100. So just by doubling the input, you are making the running time 4 times. Make sense? You're making the running time 4 times. Just imagine, if it becomes 100 times, the running time will become 10,000 times, right? Because 100 square is 10,000. So it grows pretty fast. Right? That's what I was trying to tell you. For small amount of numbers, it may not take that time. But if you increase the numbers, it will just blow up so fast that you will be looking for a more efficient algorithm. And which in this case, we're pretty sure that insertion sort is not the best, most efficient algorithm for sorting out there. What is the average case? In the average case also, you will have kind of n square number of elements, right? The elements are all randomly distributed. And in some case, you have to shift like 1. Sometimes you have to shift 4, right? If you combine all of them together, you will still get n square. But what is the best case? What is the best case for this algorithm? I think the best case is where it doesn't have to do anything. The array is already sorted, right? If the array is already sorted, then it's like it does n number of comparisons though, but it doesn't move anything anywhere. In that case, without any shifts, right? And in that case, you have omega n. It's like if you have a million numbers, you go through them only once, and doubling the number of numbers is only going to double the amount of time. But you're not doing any sorting anyway because your input array is already sorted. So now let's look at another kind of search, which is way better than binary search. Sorry, it's way better than linear search, and that's called as binary search. So in binary search, the requirement is that, and before proceeding, let me ask you, were you able to understand how we proceeded through insertion sort and how we tried to analyze the complexity of this algorithm?
Yes, sir.
Okay, cool. So let's look at this interesting searching algorithm called as binary search. Again, a very important favorite of interviewers, and even you will, come to fall in love with this algorithm, after knowing how simple this thing is. Here, the input is already sorted. The input is already sorted. So, when you give it an array and you ask it whether this one element exists in this array, the input that you have to give should already be sorted. Right? Otherwise, this is not going to work. So how this algorithm works is, so you want to see if 7 exists in this sorted array. What can you do in linear search? What would you do? In linear search,
Traverse from
traverse
image.
the array. Exactly. You traverse it from the first, and after some comparisons, you will figure this element out here. Okay. But if you're doing binary search, what you do is look at the midpoint. So here, 6 is the midpoint. Is 6 equal to 7? No. 6 is not equal to 7, but 7 happens to be bigger than 6. So what do? We discard this part of the array from 1 to 6 because that's of no use to us. Now our array of consideration is from 7 to 10. And the midpoint happens to be 9. I mean, it cannot be between 8 and 9, right? Because, well, that's nothing is there. So let's assume that our convention here is that if the number of elements is even, then we look at this element. 1 to the right of the midpoint. And is 9 equal to 7? No. 9 happens to be bigger than 7. So we discard 9 and 10, and we only look at 7 and 8. And now 8 is the midpoint, according to our convention. Is 8 equal to 7? No. But 8 happens to be bigger than 7. So now our array only has one element, and the midpoint is also that same element. And this is how we find it. It might look to you that it is almost taking the same amount of comparisons as linear search could. But take some other example here. For example, just take the example of 6. How many comparisons would it take? Just one to find out, right? Or let's just say if you're looking for the element 9, then we will be able to figure that out right here in this step. Yes, 9 is there. Then we will not go any further. Can you see how this is quicker than linear search? Each time we are dividing the array by 2 and we are trying to quickly narrow down to that element. It is not going to be linear in terms of the input. Rather, it is going to take the log base 2 of n. The worst case would be log base 2 of n. What is a log base 2 of n? It is like if there are 1024 elements, then within around 10 comparisons, you will be able to figure out if an element is there or not. Does that make sense? Because log base 2 of 1024 is 10. Because 2 raised to the power 10 equals 1024. Is that not true?
Yes, sir.
Okay. So if I just say there are 096 numbers. If there are 4096 numbers, what is the log of 4096? Well, 2 raised to the power 12, because 10 is 1024, 11 is 2048, and then 4096 is 2 raised to the power 12. So in about 12 comparisons, right? Because each time you are kind of halving the array, right? It's like you're looking at the midpoint and rejecting one half. Then you are considering the other half. Then you are cutting it into one half, then only looking at. So every time you are halving it. So in how many halves will you come to that one element? Worst case, you can find it before that also. But worst case, how many halvings you have to do? Like 4096, 2048, 1024, 512, 256, 128, 64, 32, 16, 8, 4, 2, 1. That's all. In about 12 comparisons, you will be able to narrow it down to that element, if it is actually there. But the only condition is that this input array has to be sorted. If it is not sorted, then any element can be there anywhere. It is totally random. You will have to do only linear search. Binary search is not going to work. Does that make sense to everybody? Right? So the worst case and the average case are in the order of O log of n. But what is the best case? The best case is, what you're looking for is there exactly at the middle of the input. So you do only one comparison and you're able to find it. Right? Does that make sense? Hello?
So what is better, doing a linear search or first sorting the elements and then doing a binary search?
I mean, sorting the elements, if you're using something like merge sort or quick sort, it will take around n log n. It is not n square. Like, it's not as bad as insertion sort that we just looked at. It is going to be to the order of n log n. and then you do this in log n. So overall it is going to be n log n, right? But linear is going to be just n. So I think linear is going to be better. If you do a sort and then look for the element, that is going to take more time than just doing linear sort, linear search.
Okay, sir.
Okay. So now let's take a look at something called as binary trees. So binary trees have, so any node in a binary tree can choose to have no children, one child, or two children. That's all. That's the max that they can have. And those children, they can also do the same thing. Right? That is a binary tree. So there is going to be just one root of the tree. That is the first node at the top, right? And then it can have children. The children can have their own children. There are leaves. Leaves are the bottommost. Leaves are the nodes that do not have any children, right? So both their children are null. So those are the leaves. Depth is basically the length of the path from the root to the node. So if you take any one node in that tree, so the distance from that to the root is the depth of that one particular node. And the height of the tree, so the depth is for a node. Each node will have its own depth. But the height of the tree is the depth of the deepest node. Whichever node has the highest depth, that is going to be called as the height of the tree, right? So one practical use of binary tree is a binary search tree. It's called as a BST, another favorite of interviewers, and you will also come to like this. How does this work? It works kind of very similar to how we did binary search, right? Here, as you can see, so if I want this list to be encoded as a tree, okay, so that later I should be able to search for a particular name as efficiently as possible. So what do? I create a binary tree out of this. And that binary tree will have a special property. So, and we will discover that property once we start building the tree. So we take Zara, right? And Zara becomes the root. And at this point, that is the only node, and Zara does not have any children. So they're both null. Next, we have Tim. Now, I tell you that Tim is smaller than Zara. Not because, his salary is less or something. It's because T comes before Z, right? In alphabetical order. So Tim is going to be smaller than Zara. So what we do, we put Tim as the left subtree. We make Tim the root of the left subtree of Zara. So which is the left subtree of Zara? This null, right? Whatever we put here is going to become the root of the left subtree of Zara. Subtree. The root of the entire tree is Zara. We all know that. But here is one subtree and here is another subtree. This is the left subtree. This is the right subtree, right? So we make Tim the root of the left subtree of Zara. And why do we do that? Because Tim is smaller than Zara. Then we have a Rob. Now we take Rob and we compare it with Zara. And Rob is again smaller than Zara. So Rob has to go to the left subtree of Zara. It cannot go to the right subtree, right? What can go to the right subtree? Basically nothing. Because, well, something might be able to go. If after Z here, we have like a I or something, then the Z and Z would clash and then I would be bigger than A. That might be able to go to this side. But if it is Rob, then R is clearly smaller than Z. It will try to find find some space in the left subtree here. Well, then the root of the left subtree is already taken, right? So we compare Rob with Tim, and it is MNOPQRST R, S, T. So R comes before T. So then Rob becomes the root of the left subtree of Tim, right? Are you able to understand until now? So this is a binary search tree. So here if I ask you to kind of, and there are two interesting things that happen here, right? So here if I ask you to search for a particular name, what would you do? So if I say, figure out if Mia is there. So you'd go to the root of the tree and you will see if Mia is greater than or less than Zara, right? And this kind of becomes the binary search that we were doing, right? At each level, we try to divide. But not successfully. We try to divide this input set into two halves. Like Zara should ideally divide the list into two parts. One half goes to the left part, the other half goes to the right part. It is not happening here, but ideally it should. Then once we compare our whatever we're looking for, and we see that, okay, Mia is less than Zara, so let's go and look for Mia in the left subtree. Then we compare Mia with Tim, then we just keep doing that. At some place we find Mia, right? Can you see that why this is called a binary search tree?
Yes.
Okay. But here, what is wrong with the tree? It doesn't even look like a tree. It is just looking like a list. Because, it kind of looks like a straight line. Is it going to give us log base 2 n in terms of performance, or it will more like kind of give us O of n in terms of performance?
O of n.
Why? Because even if it looks like a tree, it is a very, there is a lot of imbalance in the tree. It is an extremely skewed tree. What is a skewed tree? You look, the left side is just too deep. But the right subtree here has no element. So if I'm looking for Ava, then I'll probably do 1, 2, 3, 4, 5, 6 comparisons. And how many elements were there anyway? There were 6 elements here. So it is not going like log of n. It is going more like O of n. And why is that? Because
So it was in descending order.
Exactly. It was in descending order, right? And that's why the tree kind of became very, very skewed. As you can see, log of n is way faster than n. If n is 4096, log of n used to be like only 12. You double it, log of n will only increase by 1. You double it again, log of n increases by 1. So log of n is a way smaller number than n, right? So you don't want n performance, you want log of n performance. So from time to time, as you insert more and more elements when they come, your tree will have a tendency to go out of balance, right? One side will become deeper than the other side. So we'll have to balance the tree, rebalance the tree so that we keep the optimum performance of log n. So we will also be looking at those algorithms of how to keep a tree balanced. Right? Does that make sense? I'm just trying to give an overall picture. I mean, these are some of the toughest concepts of DSA, by the way. And if you're able to understand even a little bit of it today in the second class, just imagine you will just, have a walk in the park throughout the entire course. All right, we've got a little bit more time. So let's look at graphs now, right? So graphs can be represented in a couple of different ways in the way we do DSA. But regardless of how they're represented, you can run many algorithms on graphs. Right? The most common ones are DFS, depth first search, and breadth first search. So we kind of know what DFS is, right? So we start at a node and we try to go as deep as possible through one path until we cannot go any further. We take one step back and see, do we have any other options? If there is an option, then we again try to go as deep as possible until we cannot go any further. Then we take one step back, no options, one step back, no options, one step back. Yes, there's an option. Take that option and then go, right? And just keep doing that until all the nodes have been visited, right? Does that, ring a bell? We kind of did that while solving the maze problem yesterday. You remember that?
Yes, sir.
Yes, sir.
Mm-hmm. So to be able to do DFS, we usually use a stack. Okay. Why do you think that a stack might be useful for DFS? Because at any one point of time, whatever is there in the stack will tell you where you are in the graph. So you start at one node, you put it on the stack. Then you look for options. Okay, what other nodes are connected to you? Okay, I have these 3 nodes. Let's take the first node of yours and put it on the stack. Then whatever is there at the top of the stack, then we ask that guy, what nodes are you connected to? Oh, I'm connected to just one. Okay, fine, give it. We'll put it on the stack. Then we have 3 nodes. That means that is the path that we are at this point of time, right? Kind of gives us where we are. Then we ask that node, how many children do you have? I have none. Okay, sure. Now, visited. Then you remove that top guy. You are done. Then you come to the second guy. That guy had told us that he had only one child. That's already taken care of. Remove that. So both of them are gone. Now you come to the first level. That guy had 3 children. One of them is visited, right? That path is completely covered. You take the second one, put it on the stack, right? And just keep doing that until all the nodes have been visited, right? So you take one node. So let's just do that here. So this is a graph. Though it might look like a tree, all trees are graphs. But not all graphs are trees. Please keep this in mind. All trees are graphs, but not all graphs are trees. A tree cannot have a cycle, right? Do you see any cycles in this tree?
No.
So if I connect 4 and 5, then I will get a cycle. 2, 4, 5 will become a cycle, right? But a tree cannot have cycles, right? So a graph that does not have cycles and it is completely connected is a tree. So all trees are graphs, but not all graphs are trees. So this is a graph. It's also a tree. Okay. So let's start with node 1 and do a depth first search of this graph. So what do? We take this one, put it on the top of the stack, right? Then what do? We explore node 1, right? We say, okay, you are node 1. So we pop that node and we say, we have visited you. So we will say 1 has been visited. But when you mark something as visited, you figure out what they are connected to, and you put those nodes on the top of the stack. So when you mark 1 as visited, you then add 3 and 2, which are the nodes that 1 is connected to, right? They are the neighbors of 1, and you put it on the stack. Okay. Then what do? We pop 2 and we mark it as visited. But then while doing that, we take whatever 2 is connected to, that is 4 and 5, and we put them on top of the stack, right? So we pop 2, mark 2 as visited, but then we added the neighbors of 2, 5 and 4 here. Then what do? We pop 4, and 4 has no neighbors, so that's it. Now we look at 5, okay? So this is how we are going through the graph, right? We went to 1, then we went to 2, then we went to 4. 4 has no children, right? So then we go back to 2, then we go to 5. Then after 4 and 5 are done, we will go back to 1, then we will go to 3, then 6. 6 does not have any children. Then we go to 3 back, that is backtracking. From 3, then we again go to 7. So here we're trying to go as deep as possible. And when we have run out of options, we go one step back and then try to see, like 4, right? End here. There's the road, is closed here. What do? We go back to 2 and see, yes, can we take, do you have any other options for us? Yeah, there is 5. Okay, we will go to 5. Then after 5 is done, we go back to 2. Then we see, okay, are both of your children done? Both of your neighbors visited? Yes. Okay, then we go back to 1. Then we ask 1, quick. 2 is done. What about 3? Is 3 available? Yeah, 3 is there. Go to 3. Makes sense to everybody? Hello?
Yes, sir.
Yes, sir.
So this is how we use a stack to do it, right? We put something on top of the stack, then we remove it, we mark that as visited, and all of its neighbors are then added to the stack. Right? Then we pop something from the top, like we go one depth, one more level deep, then we mark that as visited, add its neighbors. Right? This way we kind of go as deep as possible first, and then we backtrack and we explore other options. Right? So this is DFS. So DFS, BFS, these sound very, very tough, right? People say, do you know BFS? Do you know DFS? I could solve this question that the interviewer asked by using BFS or DFS. And they kind of create this aura of difficulty and non-triviality, in the class. That BFS and DFS are really tough, but they're not actually tough. You can write this DFS thing in a matter of like 10 lines of code. And if you understand this, well, you will always be able to write DFS and BFS, even if, you're going to die at the age of 90, 5 minutes from your death. Even if you have Alzheimer's or something, you'll still be able to write DFS or BFS because it kind of becomes a part of you. Right? So let's get to the last part here. What about dynamic programming? So dynamic programming happens to be one of the toughest techniques of algorithm analysis, right? Here we take a big problem and we try to break it into sub-problems, right? And we try to figure out the most optimal solution to that sub-problem. And then we kind of extend it over the entire set to be able to get the answer, right? It also involves tabulation or memoization. So, well, recursion is completely on its own a separate paradigm, and we all know what recursion is, right? So you take a problem, you try to kind of look, are we done with the problem? Have we solved it completely? If yes, then return that answer. If not, break the problem down by a little bit, maybe solve that small part, and then delegate the bigger problem back to itself, right? So we were talking about the factorial problem yesterday. It's like 5 factorial is 5 into 4 factorial. So that multiplication part you are doing, right? 5 into something. But that something, again, you are asking the factorial function. Like, you tell me what is factorial of 4. And how do you stop it? You stop it at 1. Because, well, if they ask you what is 1 factorial, you say 1. Then that answer will be fed back to the calculation of factorial 2. The calculation of factorial 2 will be fed back to factorial 3, so on and so forth. That is recursion, right? However, if you try to solve it for, let's just say, you try to solve the Fibonacci sequence. Do you know about the Fibonacci sequence? It's like you start with 0, 1, and the third term is going to be 1 plus 0, which is 1 again. The fourth term is going to be 1 plus 1, which is 2, then 3, then, 5, so on and so forth. So the term that we're going to calculate is basically the sum of the one term before that and the term before that, right? So term n is equal to the term n minus 1 plus term n minus 2. And you begin with 0 and a 1, right? That is the Fibonacci sequence. You can do that with recursion, but that is not very efficient because, I'll then show you very soon why it is not very efficient, because you're only doing repeated calculations, right? जो आपने पहले कैलकुलेट कर लिया था उसको बार बार कैलकुलेट कर रहे हो, ये प्रॉब्लम है उसमें। और ये कैसे होता है शायद हम कोई एक दूसरे क्लास में उसको करके देखेंगे, we'll probably do it in some another class, but the thing is that it involves a lot of wasted effort. You have calculated what is the fourth term or fifth term, but if you're doing it with recursion, then you're doing it again and again and again and again and again, right? And that is very, very wasteful. But in dynamic programming, what you can do is you can store the result, write it down, so that whenever it is required again, you just reuse that result instead of computing the same thing again and again and again. So dynamic programming tends to be way more efficient than recursion. Okay. So when they ask you a dynamic programming question, so there are usually 3 ways in which you can attempt that question. First one is brute force, right? Complete brute force. Use nested loops, one loop inside another loop inside another loop. So the answer is kind of n cube, right? If you use one loop, it is n, linear. If you use one loop inside another loop, it will be n square, because each time the inner loop runs, that is n, then it has to run one more for one more iteration of the outer loop, right? So it will be n times, it will be n square. If you put 3 loops, which is not very unusual for brute force methods, it's very, very common to use 3 or 4 loops in a nested manner. So you will be going for n cube, n4, which is really inefficient, right? But still you'll be able to convince the interviewer that, okay, you have actually understood the problem statement. Then you try to solve it using recursion, because thinking recursively is kind of natural at some point. You'll become, experts at thinking recursively. Then you solve it using recursion. Even then, it will not be as efficient as the solution you'd get by using dynamic programming. If you stop there, you might still end up getting the job. But, out of 5 questions, if you solve 3 correctly, 2 not very correctly or efficiently, they might still offer you the job. But, the last thing is dynamic programming. If you're able to solve that question, if that question needs dynamic programming and you're able to solve it using dynamic programming, well, they might, probably offer you the job at the end of one question, or maybe push you to the next round of interviews just after you give that answer, right? So the Fibonacci sequence, right? Let's solve it using dynamic programming, right? This is one of the simplest cases of dynamic programming. So imagine we want to find the 5th Fibonacci number. Right? So what do? We create an array, and this is where we memorize, not memorize, memoize. It's called as memoization, right? So if you have computed something by paying a cost, store it somewhere, right? Store it somewhere. So for example, if some of you are taking notes right now, you may not have to watch the YouTube video again, right? If you have not taken notes and you're kind of sleepy right now, then you might have to repeat the efforts, right? So, which is not bad, you can still go and revise this again. So you start with a 0 and a 1 because you begin the Fibonacci sequence that way. Then you apply this formula. And how many times do you do that? 1, 2, 3, 4. So you do that 4 times and you get the 5th Fibonacci number here, right? Which is 5. But when calculating 5, did you have to recalculate everything else before? No. You just added 3 and 5, 3 and 2, and you came up to 5. It may not look like dynamic programming, but it is actually dynamic programming, right? You keep track of everything and you do it in the most efficient manner. Now think of a way in which you do this using recursion and where your efforts will be wasted. So let's just say we define a function Fibonacci, right? And we say Fibonacci of 5 is equal to Fibonacci of, so this is 0, 1, 2, 0, 1, 2, 3, 4, 5. So the 5th term, Fibonacci of the 5th is equal to Fibonacci of 4th plus Fibonacci of 3. Does that make sense? Can we write a recursive relationship like that?
Yes.
So the Fibonacci number at the 5th position is equal to the Fibonacci number at the 4th position plus the Fibonacci number at the 3rd position. So what will happen is that it will try to compute the Fibonacci number at the 4th. Then while doing that, it will compute the Fibonacci number at the 3rd and the 2nd position. Then for the 3rd, it will compute for 2nd and 1st, right? It is doing all of these things. Okay, so that is Fibonacci number at the 4th position. So what about the Fibonacci number at the 3rd position? It will do Fibonacci at 2nd and 1st. But do you already see that the Fibonacci number at the 2nd position was already computed as part of Fibonacci 4th? It was, right? But still we are doing it again. That is why just by using pure recursion, if you do Fibonacci, then it is not going to be as efficient as if you do memoization, in which you actually write it down somewhere and just reuse the result. Can you see the difference here?
Yes.
Okay. And we are almost coming to the end of this class. Sorry, it's taking a little long, but let's finish this off today. Or maybe we can do this some other time. I don't want to hold you up at this point of time. But yeah, so having gone through all of these things that you saw, we saw what we took a look at insertion sort, DFS, binary search trees. What role does balancing play? A little bit of recursion, a little bit of dynamic programming. You're able to kind of get an intuitive idea of how it is going to go in this 80 hours that we will spend, right? Yes or no?
Yes.
Yes,
Yes.
sir.
Okay. So that's exactly what I was looking for. Believe me, if you pay a little bit of attention and practice, I'll be giving you homeworks, right? You will solve it, then we will solve it in the next class. Maybe we will keep a session, another session at the evening where we only solve problems. And this is going to change your life. Mark my words. This summer is going to change your life. It will make you confident. You can get jobs and just hang on. And we'll do great things. Right. All right, then I'll post the edited video on YouTube. The first video was already there. A blog on arrays already there. You can take a look at that. It's got various questions for you to practice at different levels of difficulty. But you don't have to do that right now. I'll help you with that when we discuss the chapter on arrays, which we will do on Monday. Tomorrow there is no class. So you can enjoy your weekend. And I'll see you on Monday again. Sounds good to everybody?
Yes, sir.
Thank you, sir.
Thank you so much. Bye-bye.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Good day, sir.
Good day.